Okay, welcome back to the second morning session. Let's start on time. So the first speaker is Prem Kumar, and he will talk about replica, wormholes, and generalized Renyi entropies. The stage is yours.
Thank you very much. Thanks to the organizers for organizing such a wonderful meeting, and thanks for inviting me to present my work at this meeting. So I'm going to talk about recent work that I've done with my collaborator Tim Hollowood in Swansea and graduate student Luke Piper. And the topic is the information loss problem for black holes. And certainly, I mean, this is a problem that I don't need to motivate for this audience. The problem of how the Hawking radiation from an evaporating black hole encodes the quantum state of the matter collapsing to form a black hole has been one of the central problems in physics for the last several decades. And central to this problem is Hawking's original observation that the Hawking radiation is actually thermal in the semi-classical limit, and in particular that means that the radiation has no short-range correlations. It's thermal. And in particular, the entropy of the Hawking radiation, as you collect it, as an observer collects it at Scri+, the entropy of the Hawking radiation increases without bound. In particular, it grows unbounded. And this is the essence of the information loss puzzle. Now, to make the information loss puzzle crisp, one needs a more crisp quantitative statement. And in particular, in order to make it crisp, you need to consider the entanglement entropy, because we know that the Hawking radiation is entangled with the black hole degrees of freedom. So you need to consider the von Neumann entropy or the entanglement entropy of the reduced density matrix associated to the Hawking radiation. And the crisp formulation of the information loss problem or the information loss puzzle was given by Page. And the observation there was essentially the statement that if you consider a closed system and you consider a bipartition of a closed system and say A and B, and the entanglement entropy of the subsystem A is going to be equal to the entanglement entropy of subsystem B if the system is prepared in a pure state. And the key observation there is that the entanglement entropy of each subsystem is actually bounded by the log dimension of the Hilbert space of each subsystem. And so this means that in the thermodynamic limit, the entanglement entropy of a subsystem A is actually the min of log dimension of the Hilbert space of A and log dimension of Hilbert space of B. So this is essentially Page's theorem. And what this observation leads to is now the so-called Page curve for black holes. Because you apply this to black hole, the entanglement entropy or the von Neumann entropy of the Hawking radiation is min of the black hole entropy as a function of time, and the thermal entropy of the radiation gas collected at Scri+. So here's a typical Page curve. So this is what Page's analysis would predict if we applied this to the Schwarzschild black hole. There is kind of an assumption here that we can actually, if you look at the radiation emitted by the Schwarzschild black hole, you do spherical harmonic expansion, and if you retain the lowest harmonic, the S waves, then this is the kind of equation you get: m dot equals minus some number times temperature squared at any given point in time. And then the first law of thermodynamics, delta S black hole or ds black hole dt equals dm dt over the temperature, and then the relationship between the black hole temperature and the mass. Put these all together and you can solve for the black hole entropy evolution as a function of time. You can look at the entanglement entropy or the prediction for the entanglement entropy of the radiation as if it followed the Page curve, and this is the kind of picture that you would get. And so the Page curve here, or the Page time at which this crossover occurs, is a macroscopic time scale. It's a time scale at which the black hole is macroscopic, the entropy of the black hole is macroscopic, the entropy of the radiation is also macroscopic. So the key challenge for decades was how we could compute this entanglement entropy of the radiation in order so that it demonstrates this kind of Page curve behavior. How could you compute this from first principles? And as we know, in recent years, or a few years ago, there was significant developments that led to some progress in understanding this puzzle. And key to this, to the resolution or the proposed resolution towards this puzzle is the notion of the generalized entanglement entropy. And the generalized entanglement entropy can be thought of as some kind of a fine, sometimes people also call it a fine-grained entanglement entropy. And this was originally proposed in this particular paper by these people. And it was motivated by a precursor in the holographic context, basically proposed by these people. And this is the notion of the generalized entanglement entropy to be thought of. If you think about the holographic entanglement entropy, in this result from these authors basically tells us that the generalized entanglement entropy is the sum of an area term, which is like the Ru-Takanagi term in holography, plus a bulk term, which is an entanglement of the bulk degrees of freedom across the Ru-Takanagi surface. And then there was an extremization problem, as there is in holography. So this generalized entropy formula, which is applied to the problem of the evaporating black hole, it led to the notion of the island mechanism, which followed from the analysis done by these authors. And the island mechanism basically rests on this definition of the generalized entropy. So the idea of the generalized entropy of Hawking radiation R, or any subset of the Hawking radiation R, well, it consists of two bits. One of the bits is an area term, and the other bit is a QFT, is a standard QFT entanglement entropy term. And the way you compute the generalized entropy is actually to not just consider the QFT entanglement entropy of the radiation region alone, but to append to the radiation certain additional regions that are called islands to be determined dynamically. And every time you append these island regions, you have to add to the entropy an area term, which is the area of the boundary of this island region, and the boundary of the island region is what we call the quantum extremal surface. So the idea is to take this combination and extremize over the quantum extremal surfaces and take the minimum of this quantity over all possible island contributions. So the way this works operationally is if you think about Hawking radiation as an unroot process at the horizon, then we know that the Hawking quanta outside the horizon are maximally entangled with their purifiers inside the horizon, R tilde. And so as you collect the Hawking radiation outside the horizon at stripe plus, so here's a slice, Cauchy slice, across which we collect Hawking radiation. Because as you collect more and more radiation, as time goes by, the entanglement entropy grows because the purifiers are behind the horizon. But at some point in time, an island contribution kicks in. And the point of the island contribution is that since you're computing a QFT entropy that involves R union I, now the purifiers are actually included in this calculation, and then the entanglement entropy starts coming down in that contribution. So essentially the island plays the role of an accounting mechanism that ensures that the generalized entropy or the fine-grained entropy doesn't grow without bound. In fact, it turns around at some point. So at early times, we have a no-island saddle which dominates, and the generalized entropy is just given by the QFT entropy. At late times, an island saddle dominates, and because I gathers the purifiers of the Hawking radiation, you end up with a page curve. So that's the basic idea, and you can, of course, use this idea to understand all sorts of thought experiments in an appropriate setup, a simplified setup where you can do calculations. And in these thought experiments, you can throw in, for example, diaries and see when the information from the diary is recovered. You can check, for example, the famous Hayden-Preskill protocol, which tells you that an old black hole past the page time effectively acts like a mirror, which means that if you throw in a diary in a post-page time black hole, you recover the information almost instantaneously after a scrambling time. So all these things can be checked in very nice calculations, and several people in several groups have written all sorts of papers, including myself and my collaborators, but I don't want to talk about that. Today, what I want to talk about is the recent work where we've tried to understand basically from first principles how this generalized entropy comes about. So now the generalized entropy comes about by doing an actual replica calculation. As usual, the entanglement entropy is computed by first computing Renyi entropies and then imagining that n is a continuous parameter and then taking the n goes to 1 limit, and that's how you compute these entanglement entropies. And the question we were interested in is whether we can actually compute Renyi entropies. In other words, not rely or not look at the n goes to 1 limit, but in particular look at Renyi entropies for generic integer n. So we wanted to understand how to implement the replica trick for an evaporating black hole setup for general n. And the main motivation here is that rho, the density matrix, is Hermitian. Its eigenvalues are effectively observables, and in fact, if we can compute or trace rho to the n's, then that gives us the entanglement spectrum, which is more information than just the entanglement entropy. So our question is basically whether there is a generalized Renyi entropy, whether there's a formula for Renyi entropies that looks similar to this, where there's an area term plus a QFT term, and whether that exists for general integers, for general integers n not equal to 1. Okay, so the setup in which you can do these calculations, or one of the setups in which you can do these calculations, is in the context of JT gravity. Two-dimensional dilaton gravity. This is an effective framework. As is well known in this framework, you can view the JT gravity as an S-wave truncation of a higher dimensional gravity theory, or you can view it as the near horizon limit of a higher dimensional near extremal black hole. And this is the classical action for JT gravity, so that's the Einstein term multiplied by the dilaton and with a cosmological constant, and there's a boundary term. Now, the equations of motion of JT gravity, the equation of motion for the dilaton sets r equals -2, so the geometry is always locally ADS2, and all the dynamics, so this phi acts like a Lagrange multiplier, so all the dynamics of the theory is actually contained in the boundary term. And the dilaton in this theory plays the role of the area. Okay, so to understand black hole evaporation, you consider this is the canonical setup to consider. You think about, for example, here we have ADS2, or you can think of this as the eternal black hole in ADS2, two-sided black hole, coupled to a bath. And this bath is basically a CFT, or any massless degrees of freedom, a QFT with massless degrees of freedom, which propagate on this curved geometry, and the bath is non-gravitating. It's basically represents asymptotic Minkowski space. And so in this setup, we basically imagine that this bath is glued on with transparent boundary conditions to the ADS2 geometry. So that's the Lorentzian picture. In Euclidean, the same picture translates to Euclidean ADS2, which is basically a disk, and then embedded inside a flat CFT bath, a Euclidean bath. Okay, so this is the setup, and it is in this setup, or in this basic two-sided black hole or eternal black hole setup, that we will try to address this question. So that's the metric of ADS2. That's what the dilaton looks like, and the black hole entropy for this setup is given by the dilaton evaluated at W equals 0, which is where the horizon is, and that's black hole entropy. Okay, now suppose we wanted to compute Renyi entropies in this setup, and we wanted to imagine that we were gathering radiation. We were thinking of an interval which is the union of two disjoint intervals, one on either side of this two-sided setup. What we expect is that initially, because in the two-sided black hole, the two sides are entangled, as you collect the radiation, basically entropy will grow because of the entanglement between these two. Eventually, this entropy should saturate, and the way it saturates is through the appearance of two quantum extremal surfaces in the gravitating region inside ADS2. So if you want to think about general situations where we have general numbers of intervals, we are forced to think about a number of quantum extremal surfaces, in this case 2, but in general you want to think about doing a replica calculation where you have n quantum extremal surfaces or n punctures whose locations are determined dynamically. So in the Euclidean picture, doing the replica trick on ADS2 involves basically taking n copies of the disk, in this case 3 copies of the disk, and we have 2 quantum extremal surfaces in this example. So 2 quantum extremal surfaces, and we have branch cuts, and the disks are glued cyclically across the branch cuts. What we want to do eventually is to understand the geometry of this branched covering space. So to understand to implement the replica trick, what we want to do is understand what the geometry is of this replica space, and in particular use our understanding to actually compute the replica action or the gravity partition function in the semi-classical limit. So to understand the replica geometry, you have to use the theory of Fuchsian uniformization, something that's quite familiar in related contexts in ADS3, and it's essentially the same ideas which one can borrow from these works by authors in the context of ADS3. So determining this geometry requires one to find a map which takes this branched cover of ADS2 and maps it basically to the unit disk without any branch cuts. And the way the uniformization works is you pick one of the branch points as your reference point, and then you use a map which basically opens up or maps each of these 3 sheets into the 3 wedges that are shown in this disk. And then the other branch point and its images in the 3 sheets are basically mapped to special points in these 3 wedges. And the points above and below the branch cuts, they get mapped to arcs of circles. And as you see in this picture, there's a color coding. And the boundary conditions across the different sheets of this Riemann surface tell us how these arcs are glued together. You've got to ignore all the pieces of the arc that are outside the unit disk, basically don't exist. And then once you do the gluing, you end up with this replica wormhole geometry. So to compute the replica partition function, once you understand what this map is, what capital W is, you want to plug it into the JT gravity action. JT gravity action is a boundary term, and this boundary term is actually purely given by the Schwarzian map. It's a Schwarzian map. Basically, there is a gluing condition for the gravitating region of ADS2 with a bath, and there's a preferred time coordinate in the bath which we call tau, and the map which determines the JT action, it has to be found by solving a complicated energy balance condition. And once you know what the solution is, you plug this back in, and that gives you the action. So now there are 2 bits that are appearing in the boundary action, the Schwarzian of W with tau and T sub L. T sub L here is the Liouville stress tensor, which is defined through this map, capital W of W. And capital W is the coordinate on the covering space, whose metric is just ordinary ADS2. And the function capital W of W then determines the induced metric on the base space. And the Liouville stress tensor is also related to the conformal factor here in the metric through this usual well-known relation. Now, key point is that near the branch points, which we can think of as insertions of twist or anti-twist operators in CFT, this map has a branch point singularity. So it has singularity of this type, W minus AI to the power plus minus 1 over n, where n is the number of replicas. The plus and minus tell us whether there is a twist operator or an anti-twist operator insertion. And then this behavior of this map then tells us that the conformal factor obeys a Liouville equation with punctures or delta functions on the right-hand side with opening angles, with coefficients which tell us the opening angles. So at the location of each of the branch points, we've got a delta function source that corresponds to a conical deficit state with some opening angle. So you want to solve this Liouville equation for the conformal factor. Now, before we actually talk about the Liouville equation, there's an interesting structure already in the JT gravity equations of motion. So if you look at the Einstein equations of motion in JT gravity, very simple. They actually tell you what the dilaton is doing. So this looks like a wave equation obeyed by the dilaton. And the right-hand side, we have the expectation value of the stress tensor evaluated on the replica geometry. So the interesting thing is that, you see, because you have these delta functions here, that tells you that at the location of each of these delta functions, rho has a logarithmic singularity. Rho has a logarithmic singularity with this coefficient. And then, if you plug that in, you can check very easily that when the derivative here acts on e to the minus 2 rho, there's going to be a simple pole. So you can look at the residues of the simple pole of the left-hand side and the right-hand side. The residue of the simple pole on the right-hand side is constrained by CFT word identity, and it gives you exactly the derivative of the CFT Renyi entropy with respect to one of the branch points. But the left-hand side, on the other hand, when you evaluate the residue at one of these branch points, gives you precisely del W of phi evaluated at W equals AJ, the derivative of the dilaton evaluated at a branch point. This looks almost exactly like the quantum extremal surface condition, but it's only superficially similar because it tells us what it involves is not the derivative of the dilaton with respect to the branch point locations, but rather it's the derivative of the dilaton evaluated at the branch point location. So the real question here is, how is the derivative of the dilaton evaluated at the branch point related to the derivative of the dilaton at the branch point with respect to the branch point? These are two completely different things. So in order to understand this, you first look at the one quantum extremal surface problem. The one quantum extremal surface problem is actually quite trivial, but it's quite instructive and interesting. So in the one quantum extremal surface problem, there's just one branch point here, and we all know how to take the disk, the n-fold covering of the disk to the unit disk. It's through this map. And the dilaton, it turns out, has a very nice looking integral representation on the unit disk. So you can look at the equation of motion of the dilaton, invert it, and do some manipulations, and then discover that the dilaton can be interpreted as, can be written as an integral representation, as an integral over the boundary of this disk. And on the boundary, you can then use this, inside this integral, you can then plug in the uniformization map, and then after a bit of manipulations, you discover this miraculous relation that del W phi W at W equals A is n plus halves del A phi A. So that then tells you that the conformal word identities and dilaton equations on the Einstein equations of motion actually imply a quantum extremal surface condition for general n. And this quantum extremal surface condition for general n, it also follows by actually taking the gravity action plus the CFT action and extremizing it with respect to A. Both processes give you exactly the same condition, and so you can identify this combination as the generalized entropy for any integer n. And what this really is, if you note carefully, you see this is Sn CFT is the Renyi entropy of the CFT, but it's multiplied by a factor 2 over n plus 1. If you look carefully, the Sn CFT is a universal result. This is a single branch point problem, and this involves basically the single interval entanglement entropy, which is a universal object. When you multiply it by 2 over n plus 1, the quantity that you get is what's called the modular entropy. The modular entropy is essentially thinking of the replica partition function, the log of it, as a free energy, and then computing and pretending that it's actually a thermodynamic free energy, and thinking of 1 over n as the temperature, and then finding what the entropy then would be. So this combination is the generalized modular entropy, and this is the natural object that appears for generic integer n. And this is actually quite nice because it's consistent with a prediction of Dong, with a calculation of Dong in the holographic context. Dong in 2016 tried to answer this question of what is the generalized holographic Renyi entropy, and he ended up precisely with the modular entropy. So I'll try to finish quickly through the rest of the slides. You can now try and generalize this question for a general number of branch points, and the problem becomes actually quite non-trivial because unlike the n goes to 1 limit, which is very special, where all these branch points or conical deficit states are like probes propagating in a geometry. In the n, away from the n equals 1 limit, these different conical deficit states or branch points, they interact with each other. There's a back reaction effect. And this back reaction is generically non-trivial. To actually solve it, you have to solve the uniformization problem. This is actually quite well known. You have to solve for the uniformization map, capital W of W, by solving this auxiliary Schrodinger equation, whose potential is the Liouville stress tensor. Almost done. Liouville stress tensor, and the key in this uniformization problem is to determine these accessory parameters. And it's these accessory parameters that actually eventually determine what the replica action is and what the generalized entropy is. So this can be done. So you can show that the replica partition function in some high temperature limit depends only on these accessory parameters, which can actually be found. So in the example where you have 2 branch points, and precisely, where the replica number is 2 and where you have 2 quantum extremal surfaces, turns out the problem is elliptic, and you can show that this domain, this fundamental domain here, is actually a strip on the torus. You can do a lot more. You can actually find that you can find the metric on this. You can show that this metric on this surface corresponds to the double trumpet metric. So it's the trivial wormhole with 2 boundaries. And you can compute the replica action exactly in terms of some complete elliptic functions. You can do this also for general number of, for general replica number and general number of branch points, in which case the replica partition function is related to some semi-classical conformal block in Liouville theory. The upshot of all this is that the notion of generalized entropy for general number of quantum extremal surfaces looks like the standard generalized entropy formula, except that now you have to interpret it as a generalized modular entropy. But there are non-trivial corrections which correspond to interactions between these different branch points. In the late time limit, when these quantum extremal surfaces and islands dominate the entropy, these corrections actually are small. So that's the summary, and there are some open questions. Thanks for your attention.
Thanks for this nice talk. Are there questions? Over here.
Yeah, so you derived that equation that looked like a quantum extremal surface condition, and you derived that from geometric gravity, right? Can you also do that with something like CGHS model?
Presumably.
Okay.
I haven't thought about it, but yes, that could well be
I have another question.
Yeah.
So in the very start of the slides, you said that the radiation entropy is 2 times the difference of the black hole entropy at the starting time and at time t. You had this factor of 2 there that I didn't understand why you have that factor of 2.
Oh, sorry. I mean, that just happens to be numerical.
This one, yeah.
Or that just happens to be an observation. You can compute the radiation entropy, and you can check that actually it satisfies that relation. I don't think there is a.
Okay.
Yeah.
Thank you.
Here we have another question.
So in general, when you have a standard Renyi entropy, another holographic way to compute the standard Renyi entropy is to use this Cassini-Huerta-Myers map, where you can compute it as the area entropy of an hyperbolic geometry. Have you thought about some modification?
Well, so that's actually a good question, because that's what Dong was doing when he was actually looking at the, say, multiple intervals, Renyi entropies for multiple intervals. And in that case, that's exactly what he was doing. And in fact, in his calculation, in the appendix of his paper, he has a calculation where he tries to find these corrections that come. There is a sum of the Renyi entropies, and there are correction terms. So I think it is actually an interesting, that's one of the to-do exercises for us, to understand whether the corrections that we can get, we can actually compute them in some cases, whether they can be compared with the holographic entanglement entropy corrections through that approach. Yes.
Thank you.
Is there, I see another question over here.
So you have these extra small terms that correct. Do you understand them at least in an n-1 expansion?
In principle, yes. We haven't tried to completely do that in the n-1. We actually try to understand it in the small x expansion. So there we do have them. Yeah, we were not. That's a very good question, because one of the things to check is if you can get them analytically. You want to check that they're actually higher order in n-1, which, yes, there are some indications from the calculations that we have done that suggest that. But it's actually a hard problem, because I think the place where we can do that precisely is in this elliptic case, where we know everything and we can compute it and we can try and do this. In general, it's harder to do because there is this integral representation for the dilaton as an integral over the boundary, and there are these extra circles. And what we don't know exactly is what contributions these extra cutout circles in the Fuchsian uniformization problem, what extra contributions they give. They are very hard to compute in general. But that's where the information is on those small terms. Yes. Yeah.
Can I have another quick question? So did you think about, so you did your calculation in Euclidean. Have you thought about what's the Lorentzian?
Yes, very much. And that's going to be in fact, that was our motivation, to actually understand what the Renyi entropy is and do this in the Lorentzian setup. And actually there are quite a few pitfalls straight from the start, because you can think of this Euclidean setup as like setting the initial state and then you sort of evolve. Problem is that once you go to Lorentzian, putting these punctures and going away from the n=1 limit actually introduces shockwave singularities. Okay, so that's a problem that we have to deal with, and so it's not yet resolved. Yeah.
Okay, let's postpone all further questions to the later breaks, and let's thank him again.
Thank you.
Very nice.